And of course, if you want, you're welcome to mention those as well. But it's a pleasure to have you. Thank you.
Wonderful. Yeah, thank you for having me here. I'm going to focus today just on the knitting research, but I'll first introduce my lab. We're the Accessible Creative Technologies Lab. So we focus on creative technology, so any kind of technology that enables particularly digital fabrication or craft, but also accessibility. So a lot of the other work in my lab is focused on people with disabilities and medical devices and the intersection of these two spaces. So I want to start off by kind of talking about knitting and the perspective that I have coming into the knitting space. When we think of knitting, we think of what you've lovely demonstrated, this kind of what machine knitters will often refer to as the sticks method, where you're knitting with 2 needles and creating a bunch of loops to form a textile. But most of what the work in real knitting in the manufacturing space is using industrial machines, like these whole garment machines here. And I like to think of these machines as kind of a symphony of needles and yarns orchestrated by what we call carriage passes. And that white object moving across the bottom of the screen is what we call the carriage.
Are you implying that these machines do fundamentally different from what it's doing?
They produce a similar structure, or they can produce similar structures. These do some structures better than hand knitting, and hand knitting does some structures better than this. But they are using a fundamentally different mechanism to do the same process. Now, these machines are deployed across the world. They are kind of one of the main components of textile manufacturing globally, and they produce all sorts of things that we're very familiar with, like sweaters and socks and hats, and every essentially fast fashion, stretchy item you've ever owned was probably built on a machine like this. I mean, there's hand-knitted items, but there's not really any kind of knitted, like manufactured structures that are not made on a machine that uses these properties. There are some other types of knitting machines for non-garment processes, but I'm not going to be talking about those today. At the basis of knitting is the idea that you can form a structure of loops pulled through loops. So we imagine we have this white loop of yarn, and if you were to pull on either end of it, you no longer have a loop of yarn, you have a like taut piece of string. But if you pull another loop through it, like this gray loop here, and then you pulled on the ends of that white loop again, you've stabilized that structure because it's now pulling on the loop above it, and you've got a stable fabric structure. And you can build up a knitted texture or garment or textile by just doing this like loop through loop structure. You can change the properties of how you pull loops through one another. This most simple way is to change the direction that you pull loops from one end. Hand knitters will call this knitting and purling, and it creates the basis of the textures of a knitted structure. And you can create whole patterns using this and control the physical properties of your textile. So alternating knits and purls to create what we call ribbing, which if you're wearing a sweater, you probably have on the cuff of your sweater, or creating these kind of gartered structures that curl or don't curl and stretch in different ways. You can also use this process in a manufacturing method to create really complex 3D structures at a very large scale. So we can make architectural elements like these elements here, or we can change the metamaterial structures to kind of embed different properties into mechanisms. So making this kind of self-folding lampshade that is done by Shimaseki, the manufacturer of the knitting machines that I use, these different kinds of textured properties embedded into garments like this bag here, or kind of functional properties like ones we might see in a running shoe or other types of athletic wear. And then finally, by changing the material properties of the yarn itself, we can kind of integrate different types of interactive materials. Most people in this space are exploring e-textiles, integrating conductive materials to create interactive elements. And I've also done some work where we're using actuating fibers so that we can make the fabric interact itself. And the interplay between the structure of the knitting, that loop through loop relationship, and the materials you choose can create a wide variety of different designs. And over the past few years, there's been a lot of interest in that interplay. There's been a lot of advances in knitted e-textile work, mostly focusing on different kind of soft robotic mechanisms. Now, for me, the most interesting challenge in the space and what my lab particularly focuses on in the knitting space is trying to support all of those new advances, all of that complexity, without relying on the existing tools that people have to interact with these machines. So this is what a kind of standard machine knitting interface looks like. We'll talk about it a little bit later in the talk, how you kind of process and get from this image here to this glove. but this is a very bad representation of the knitted structure that's very focused on instructions, the machine level operations, rather than the knitted structure itself. And so I'm going to talk to you today about two projects. One was my first research project in this area, and the latter was kind of my most recent research project in this area, looking at how we can use the representation of knitted structures to facilitate the design of more advanced tools. We'll start off by talking about texture and metamaterial design and the construction of knit graphs, which are a loop-based graph structure for connecting stitches. So again, we return to this figure of the knitted texture, and from this we can derive a knit graph structure where we have loops as nodes connected by yarn edges so that we can keep track of where the loops are along the yarns that create up the fabric, and then as well as stitch edges, which retain the properties of the direction that loops are pulled through one another. And from this, we can derive all of the information we need to understand a knitted structure. So one simple application of this that is important for building a metamaterial is to think about the curling property of knitted structures. Knitted fabrics tend to curl, and the reason that they do this is that loops are essentially sitting on top of each other. And if you pull them through the same direction over and over and over again, they're just going to kind of sit on top of each other and form a curling pattern.
So it's a curve to see curvature.
Yeah, or like it rolls up, like a piece of fabric that rolls up like a scroll. So yeah, that kind of curvature. So if we have this knit graph structure, we can find any particular child loop and the parent loops that it's pulled through. And from that, we can figure out whether or not it curls, it's going to curl in a positive or a negative direction based off of the orientation. And then we can recursively define this function to figure out how much it's going to affect the fabric overall by kind of looking at this over time with a decaying factor based off of the material properties of the yarn itself. And from this, we can estimate how much an entire fabric is going to curl by taking the average curvature of a single wale, so a column of those stitches, across a given row, because they're going to compete with one another. If you have two competing columns that are alternating in different directions, they're going to zero out that curvature. And this is what creates common patterns like that ribbed cuff I was talking about on your sweater sleeve.
So the local curvature keeps it whole.
Exactly. We can also use this intuition, mostly coming from hand knitters, but then validated in these kinds of simple models, to show that we can modify a design automatically to include these kind of properties like curl. So for example, if we have the intuition that knit stitches are going to curl one direction and purl stitches are going to curl another direction, then you can start to design those patterns to create different things. So we have the alternating columns, which are going to average out to not have any curl. We can have uniform curl accumulation by having everything all aligned in one direction, or we can alternate rows to cancel out and flatten the fabric. So following on this development of knit graph structures, I was able to apply a framework from my other research around meta-heuristic optimization and toolkits for end-user generative design to support generative design of these textile structures. And we include beyond curl, things like stretch and compression, as well as other aesthetic properties like cabling, lace patterns, colorwork, etc. We can generate all of these through a simple representation of a designer's objectives, what they want to see in their knitted structure, and their kind of heuristic example of setting this up. From the knit graph structure, we can include a bunch of modifications at the node level. We could say, let's introduce an increase or a decrease pair by joining two loops together in a stitch or separating two loops out. We can cross stitches over one another, so changing the orientation of the yarns to form a cable. We're going to align child and parents in that kind of knit and purl pattern, or we can move them, or we can flip the stitch orientation. And from this, we can specify new objectives to create this textured pattern. So we might want to say, okay, I want some columns of lacy eyelets so that we can let a little bit of light shine through our lampshade. We can form columns of cabled stitches to give a particular aesthetic motif. And we want to curl the bottom and top edges so that it curls around the wire frame of the lampshade so it holds onto itself without any additional stitching. And then we associate these with the different heuristics that we've assigned. And through that optimization toolkit, I'm not going to go into super detail about, we're able to build essentially a simulated annealing process to apply these over time and then generate this particular structure.
In these machine knits, is there one piece of yarn or are there multiple?
There's multiple pieces of yarn. Yeah, this one is actually hand knit because I was doing the research and like, I think I built the system in February of 2020, and you can imagine what happened in March when I needed to make samples for the paper. But it's the same structural component here.
So is the craft organization, do you know yarn edges that are distinct yarns from one another, or do all yarn edges?
So a property of the yarn edges is what yarn they belong to. So that way you can kind of associate which ones are associated with individual yarns. And that's particularly important when you do things like color work, or what I like to think is my favorite color is conductive. So incorporating in those kind of functional components as well. Yeah. All right. So that gives you an intuition of like one place we can use knit graphs from. There's been a lot of work since then adapting this particularly simple representation to create different generative design tools, or expanding it to spaces like creating 3D models of knitted structures. My most recent work is now expanding on a different representation that helps us get quickly between this kind of understanding of what we are knitting and how we are going to knit it. And this is instruction-based dependency graphs. And to understand these, we're going to go back to that symphony of needles and yarns orchestrated by carriage passes. I'm going to kind of walk you through the basic intuition of how a knitting machine goes about this process. So the first piece of a knitting machine is that we have two sets of front and back needles that are aligned with each other. Things that we knit on the front bed are going to create knit stitches. Things that we knit on the back bed are going to create purl stitches. And you can kind of rearrange things on those needle beds to create different structures. The carriage is what actuates these needles, allowing them to do all of these different operations, and they move in a leftward and rightward rotation, like so. And then if we want to create this initial loop of yarn, we're going to do what we call a tuck stitch. So these needles are going to take a loop that passes by them and put it onto the needle, just kind of hooking it on there and holding it in place until it's knitted through. And by creating a series of these operations with a yarn carrier, we're able to create our first set of stitches. So we're kind of laying out the basis of the yarn. Yep. Yep, that's all embedded in a single tuck operation. Now, if we want to pull loops through each other, we're going to do a knit stitch, which both creates a loop and pulls it through any of the loops that are pre-existing on that needle. It's doing this kind of structure here. And so if we take that carriage pass and go back over, we've dropped our original loops, pulled new loops through it. We've got a very simple structure. And again, we can change the orientation of these stitches to be knits and purls based off of their location on the needle beds. And in order to rearrange our loops so that we can do knitting and purling, we use transfer operations to pass loops from the front bed to the back bed or vice versa. So we might want to purl the 6 and the 7 loop here by transferring them to the back bed and then knitting over them. By combining a bunch of transfer operations, we can create all sorts of complex structures. So in particular, we can create cable structures, which are represented by art and braid groups. Essentially the idea of changing the orientation of how these loops cross over one another. And we do this with racking instructions, where we realign the beds relative to one another so that we can change that positioning. A simple example of how we use this is to create something like an increase or create space for a new loop. So we take one loop, pass it to the back bed, move it over, and then pass it back over so that we've got this empty needle in the middle. Or we can decrease loops by moving them to be aligned with one another by passing to the back bed, shifting over and putting it on another loop so that when we then knit through those loops, we're going to create 2 stitch edges going into the same child loop. And with all that intuition in your head, you can now start to understand this very terrible design tool. So the intuition behind these designs is that each of these pixels represent a single operation in time. So each of the colors actually is coded to a particular operation. They don't mean anything about the color of the yarns. So for example, these green stitches mean that you're going to knit from the needles 1 to N on the back bed, and these pink squares are going to have us knit on the pixel on the front bed from needles 1 to N. And the position of those pixels tells us which needle we're applying an operation on, and the process goes up from bottom to top.
And you're free any color in any dot because there are no dependent systems.
Yeah, and so you can.
It's a vocabulary.
Yeah, it's a vocabulary, and you can do. It will let you do all sorts of things. The vast majority of combinations of operations will not produce a knitted structure. So this is really.
So that there are then inline
Absolutely.
Okay.
And the system does not do much to kind of help you understand those invalid operations up front.
When you're reading this, you read just the thing in the middle, or do all these bars on the side, are those also operations that are happening at the same time every time?
The bars on the sides are parameters of your operations. Very intuitive. You have to memorize the colored bars are always there. They tell you what parameter you're changing. You're just supposed to remember that. You're going in a zigzag, actually. So you start from the bottom, you move from left to right, right to left to right, right to left, upwards. And that alternating white and blue tells you which direction the carriage is moving. Again, not good. This is a terrible way to design complex structures or even really simple objects. So the first step to move away from something like this into something that's kind of more compatible with thinking about knit graphs and how people might actually design a complex object is to give us an assembly language to really simplify this all down. And so McCann et al., collaborators I have from the same textiles lab, created the knit out language, which is a kind of a summary version of all of the operations you could apply on this machine that can be directly compiled into this MS Paint style assembly language. So some examples here would be to say, we inhook yarn 1, which brings in the first yarn into the machine. We then do some tuck operations on specific needles. So we're adding some loops in. We do a release hook, which essentially cuts the tail of the yarn, allowing the machine to continue operating. You do some transfers to move things around and rackings to move things around. And then you finally knit through them. This will create a simple decrease structure. I've developed a more advanced scripting language that facilitates this, but even with these assembly structures and the scripting language on top of it, your intuition as particularly a hand knitter is not going to lead you to the most efficient knitting operations. It means you're going to waste a lot of machine time, but also inefficient knitting will often strain the yarn in such a way that you're essentially not going to be able to effectively produce a complex structure. So here we might have the intuition of moving a loop backwards and forwards to create those decreases like I showed you before. But if you do this one by one and step by step, you're essentially going to wear out the yarns that are sitting on those loops over time and get a bunch of yarns that tear and fall apart. So an intuitive program might look something like this, where each of these black sections are going to create kind of wasted time, space that the machine is just sitting idle, not doing anything. And this will produce a single row of cables. And then all the rest of this is wasted time that's straining all of your fabric. What I've developed is a dependency analysis method for optimizing these programs. So you can write your knitting algorithm in an intuitive way, but still get a more efficient output. And so what this does is it rearranges instructions in order to maintain the dependencies between different instructions in such a way that you're going to have the optimal result. It's going to something
Existing things.
No. No.
They just have
By hand. They're called knit programmers in the industry, but they don't often see themselves as kind of aligned with like the rest of the programming world. They can make a lot of money. It's a very, very rare skill, and particularly for doing some more complex textile engineering, requires a great deal of expertise and training, but a lot of it is just pixel by pixel editing. So we get the 7 rows of cables here. Now, knitted structures, the intuition behind this optimization structure is that we're going to kind of build up by processing out a knit out structure. We're going to build up a knit graph and a dependency graph at the same time. The dependency graph has nodes which are operations, so each operation we pass, and the knit graph is just going to be built by a virtual knitting machine as we're knitting through it. So let's say we add some tuck operations. We're going to create those different loops that result from the tucks, and we're going to create some corresponding tuck operations with a yarn order dependency between them, essentially saying that these have to happen one after the other because the yarns between these loops must move in a certain order in order to create the same structure. We can then add some transfer operations in this kind of step-by-step process. So moving a stitch over to the back bed, that's going to create a transfer operation, but doesn't change anything in our knit graph quite yet. And we have a loop position dependency where that tuck operation create a loop, and then there's a dependency of that loop having been created before the transfer operation can move it. And then finally, we can add some knit stitches in, and this will create stitch level dependencies. So again, we have some yarn dependencies from the tuck operation to knitting operation, because we're using the same yarn. We create these two knitting operations in the dependency graph, and we have stitch operations between them and their tucks, because they have to knit through the loops that the tucks made in order to process. We also have a loop position dependency going from our transfer to our knitting operation on the first knit, because that transfer operation moved the loop and it has to be in that specific position in order to create that stitch. And then we can repeat this process, creating some more transfers and then some more knitting, and get this similar structure in our dependency graph. Now, if we follow this operations in the original pattern created by the programmer, we're going to get some inefficiencies here. We have our first carriage pass of all of our tucks, and then we're going to have these transfers, which create their own independent carriage passes, followed by a knitting carriage pass, followed by another carriage pass for the next transfer, and then followed by two more knit stitches in that fifth carriage pass. But if we look at the topological order of this structure and we look at the layers of the topology, we can see a different pattern arrive, which allows us to get a more optimal knitting procedure. And so specifically, we identify that there's a layer in the topological ordering of these transfers, which can give us a second consolidated carriage pass. And that the outcome of that is that all of the knitted stitches in the next layer are going to be consolidated into another. And so we've reduced the carriage passes down. And this is a pretty small modification for this number of stitches, but you can observe these patterns over a very large structure and end up reducing the pattern down to by at least tenfold in the cases where you have these kind of stitch by stitch patterns. We validated this with a bunch of kind of randomized and pre-generated benchmarks, applying a bunch of structures, including increases, decreases, cables, and color work. And so we were able to show that this frees up more complexity for knit programmers who want to use these intuitive algorithms to do the machine knitting, but still need the optimal results in order to manufacture them.
Explain us, what do we see here? How do we know that work or not?
So the simple answer to how these worked is we tried to knit the ones pre-optimization, and you can't, they just break.
So it's not that the top is free and the bottom is after.
Yeah, so these are just some samples that we produced. We needed.
You wanted to knit and you succeeded.
Yeah.
And we do seem to see some errors and stuff like that in the lines. Is that intentional? You wanted to do that?
Errors in the lines, like these kind of patterns. Yeah, so these are randomized cable patterns. So the stitches are moving, we call them a traveling stitch, across the pattern in a random orientation. So
this is on purpose. These are not errors.
Yeah, okay. Exactly. All right. Some things that I didn't get to talk about that I think this group might find some interest in. There's a lot of focus, particularly in the graphics community, on machine knitting, focused on machine knitting arbitrary 3D meshes. So I've been collaborating with some folks at Boston University who are interested in this space, essentially coming up with different planning or different ways of transitioning from a traditional 3D mesh into a knit graph structure, and how we can optimize those meshes so that they'll produce knit graph structures that are efficiently knittable or intuitively knittable. This is always a space I was very skeptical of, because most of the applications here are for the people who will propose are like taking a 3D scan of your body and knitting a perfectly fitted sweater. But most people don't want cat suits. Go ahead. Again, the same, textile designers actually call this ease. You actually want a little bit of spacing between your garment and your body. And so that's something that's kind of built into the existing patterns in a way that a 3D model will not quite work out with.
You don't think of clothing that you want to knit yourself. Can you make an identical copy of yourself?
If you have a good model of yourself, then definitely. We've exactly. So they've been able to do that, but the real world applications were always something I was a little confused about. But we've actually got some collaborations starting up with a company in Boston who does composite knitting. So they'll create complex 3D structures of like airplane wings or boat components or something like that, create them with a knitted structure, and then use that to create a composite form. And so they really care about these very precise 3D knittable shapes. So there's a lot of promise here in that space. And then as we start to incorporate more materials or novel materials into the knitting space, we have new opportunities to kind of expand these representations. So far I've talked about the relationship between yarns and stitches, but this gets particularly important when we think about things like actuating materials. The white fiber here is a heat-sensitive material which will shrink in contact with heat and then change shape back to its original form as it cools down. And so being able to model these properties of knitted structures is of particular interest. And there's emerging work in machine knitting spaces and the manufacturing process itself to create not just 3D knit surfaces, but full voxelated surfaces, which are going to call for yet more representations or thoughts about the kind of relationship between knit stitches.
What would be the application for that? Oh, I guess like you like the bottom of the shoe stuff.
Yeah, so this gives you a way of manufacturing any kind of soft material or fabric-based material in a fully 3D volume, as opposed to what most textile applications are now, which is a 2D surface that we like wrap or conform onto another object.
That would require specialized, like the existing knitting machines would not be.
Yeah, not able to. To date, there's 2 machines that can do this, and they're both in the very early research stages. They can only make very small objects. So there's a lot of interest there.
The looping pattern, like the idea of just loops going in loops, essentially the same 3D volume.
It is, but they have a lot more. You're going back through other loops in new ways, which creates new complexities. Yeah.
And these machines don't use it in graph.
They don't. So the 2 3D knitting, voxelized knitting projects that I'm aware of out there are still at the stage of just building the machine and kind of hand programming all of their operations. They're working on very small scales right now. So, but I'm in conversations with those folks about like what's the representation of these going forward when they get to a machine that's good enough that we just want to start building design tools around it.
Have you looked at what kind of patterns improve the durability of textiles, for example, or this kind of optimization enhances the maintenance time of the machines?
We haven't yet, mainly because we're not producing textiles at the same level as like a manufacturer would, and so it's hard for us to compare our tools, which are kind of only used by researchers, to their industrial methods. A little bit of the answer on maintenance time of the machines, these are really reliable machines. Like the engineers who built knitting machines have just really got that tuning down. They just don't know how to build software. And so there isn't much need in that space to kind of further, like these are already more reliable than like equivalent for weaving or other textile manufacturing methods. There's not much desire to improve the reliability of the machine operation. In terms of the textiles itself, we have kind of 2 goals here, is that you can expand the complexity of what people create because people are already limited to such simple designs, or like the places that are essentially intuitive to design and already optimal or manufacturable. And they're limited by the types of kind of what's already been done. A lot of people are just copying other people's models and modifying them in very small ways. So giving us this optimization process allows us to more quickly explore new spaces where we don't want to think about like, what's the optimal way to knit this new complex structure.
And there's a follow-up to that. In this graph representation, like there's different patterns of your knit may create different durability.
Yeah.
Textile. Will you see those differences in of the graph representation, like a different graph structure getting associated with different properties or things like that? Expect that to occur or not?
I mean, there are kind of patterns that machine knitters understand are going to be more durable, and you could easily figure out how to detect those from these structures. So a basic example of this might be that if you have a bunch of loops overlapping one another, so you're just stitching through a bunch of loops all together, that has a tendency to either drop one loop off of a needle or just create a lot of strain on the fabric that's going to tear later on. And you can easily detect that by building kind of constraints into your graph structure, saying, hey, you're knitting too many loops, you have too many edges going into the same node. This is probably not a desirable property. You want to change your design in some way or automatically rearrange it to not have those properties.
I mean, this is really cool, and I'm trying to figure this out. That so you're somewhere, the mathematics of this one is somewhere at the interface of combinatorics, topology, and graph theory, right?
Mm-hmm.
So are people doing theorems for this, or do they exist for like 100 years or something? Because after all, knitting gave rise to computers in some ways, right?
Yeah.
So do they exist, or is it just baked
So the kind of focus on this as a mathematical principle is relatively new, at least in the like programming and the design space of it. The history of computing you're referring to is actually for weaving, which is a very different structure. Not quite as correlated there, but the weaving is an over-under operation. So you've got a bunch of yarns in either the kind of horizontal or vertical direction that overlap one another. So a good example is like the chair you're sitting on is woven, but your sweater is a knitted structure.
Yes. Most of us mortals don't know there's a difference, but I hear it.
Yeah, I see those differences a lot now. You kind of never get to escape them. There are some folks who are doing kind of more of the like theorem proving work. So in particular, Jenny Lin is a researcher in this space who's really got that focus. I had showed an example here of what she refers to as art and braid group orientations of knitted structures. So she's really coming up with these kind of representations and then using them to prove theorems about like how much can you optimize a knitted structure, how can you validate a knitted structure, things like that. A lot of the work I do is kind of have a good synergy with her of taking her theory and putting it into practice in these tools.
And I'm assuming that AI is coming this way, right? Because you try to kind of shortcut some of these traditional searches, right? Is that something that you're using, or you're still more like a form of programming?
Most of what I'm focused on is on the programming level, because that's just like we need to build those tools in order to combine this with existing AI methods. But we've certainly applied like kind of classic methods before, so that meta-heuristic optimization is an example. Generative AI here is going to be tricky because you kind of need a data set of some kind or some place to source an embedding from. And there's just not a lot of data. Like you can't take the designs that exist in the machine knitting space by professionals because they've not been like transferred into our tool sets. So they don't get knit graphs out of result. Yeah.
Because at the end, it's like sentences, right?
Yeah.
So you could just go ahead and
sample a bunch of them.
Yes, yes. But they're not in the public domain, and not enough is in the public domain to actually use them as training.
Exactly.
Yeah.
Is that the issue with public knowledge?
Both. Yeah.
Interesting.
Do you have an easy pipeline for something?
Not backwards. I mean, which is mostly just because we haven't built a reverse compiler from the terrible MS Paint version because I don't want to. But it's theoretically quite possible.
But yeah, but could it be that we would actually scan my shirt and then put a different program and then we'll tell you the code?
You can't do that quite yet. So you can do, there are tools out there for kind of taking 3D models and turning them in. So you can take a scan and put that in, and it will give you code that should be able to make something like your shirt. But there's a lot of kind of bugs in that process or complexities of like one 3D representation of your shirt is not the same as the next because the wrinkles will change. Should it try to represent those or should it smooth it out?
You kind of smooth it out, right? So not like very, but smooth it out, take a centimeter by centimeter high resolution scan of that.
Yeah.
Should you not be able to reproduce that?
You should be able to reproduce the knit graph from something like that. No one's focused on that particular problem, but it should be possible. But we don't have, but as soon as you add some more complexities into it, it quickly becomes this kind of compounding thing of like, if your sweater has multiple colors and we can't see all of the relationships between the yarn on the front and back side or something like that, you're just missing a lot of data to process these out.
The final question is that, so like in design, right? So you come up with a cool knitted sweater that you want to show for the next variation. So how does that go from the designer mind to sweater? So what are the steps to that? Right?
So for most designers, the answer is that they give a sketch and a Pinterest board to a knit programmer who is going to meticulous. Yeah, there are some people out there who are both designers and knit programmers, but that's a pretty rare combination of skills. But it's this very manual process. Like, it just has not been digitized. There's no CAD tools that really facilitate a lot of this. There's some things around like simulating a fabric and like visualizing them, but they're not very good. And most designers I've talked to don't use that software just because they find it to be extremely like limiting. It only shows you some patterns, but not all patterns. It doesn't enable the kind of complexity they're looking for.
And these are the designers that we think right? Yeah. And do they exist? Is this like a widespread profession or?
Relatively rare, and the majority of them are in countries where the manufacturing is based. So the majority of them are in places like Bangladesh, where a lot of our textile manufacturing happens globally. And so there's also that transfer problem a lot of times. So
you just can't call somebody from Boston from the street to say, hey, you are a designer, let's just work.
Yeah, not too many of them out there. Yeah.
Are there any? Other than you?
There are. So actually the Cambridge Science Festival this year had a day on textiles of the future, and I hosted a panel. So there were a number of Boston-based designers who do this. There's in the United States, the majority of these people live in New York and LA, which is kind of where our fashion design hubs are, but it's still pretty rare to find it.
Any other questions? Well, then let's end by good. I have lots more questions. Happens end of the week, right? To think about knitting.
Yeah, I'd love to hear more about what you guys.
Sure. How much time do you have? What's your time?
Until the end of the workday, I'm
okay,
totally free.
Right.
So.
I'll let you, if anybody wants to ask you questions, then they can do that. Then after that, in my office chat, and then we'll really.
I'll leave the Zoom call and.
Hi.
In a past life, I did work on material science stuff, and a lot of this knitting reminds me of like sluggerty in some sense. They have like specific lattices that either align in certain places or don't. I guess when someone talked about like failure modes for these materials, I was thinking about around seams it's very common for things to fail. They don't really fail in the middle of a I guess I'm curious, like how do your knit graphs feel about representing those? I know in the pixel grid you had, it wouldn't be very obvious there's some kind of border between patterns.
Yeah, seaming. So this is actually one of the desirable properties of more advanced machine knitting techniques is you can make whole garments without seams. And so the kind of idea here is you've got the right intuition, like seams are the most unreliable place. Usually there's kind of two layers of representation of a full garment. If you do seaming, there's a lot of existing work on like representing kind of how you seam together multiple textiles. And so we would probably take do a knitted representation, and then you do a representation of like all the panels that you've knit on top of it. They're not often like, because when you're seaming things, you're not being really careful to like seam through the same loop or loop structure. So you kind of just treat it as a fabric at that point. But one of our main goals kind of in terms of sustainability of textile manufacturing is that if it were easier for people to actually design a whole garment, not just the machine being able to do it, we might get more garments that are whole garment, and then they're not going to be as likely to fail on seams, and this might reduce the textile waste or support reuse or things like that. So it's like always a disappointment to me of like, this sweater has seams here, but there's no reason that this machine was not capable of making this without any seaming at all. And so that's a limitation of the designers, but not the equipment.
That makes sense. I guess the other part was that I was mildly aware that my mom is sort of a obvious seamstress, but I think some of these things, like some of the defects we talked about, are like very useful for either modifying garments. Like it would be very hard to modify something with this, I think.
Yeah.
I don't know, like how much do you think it's useful to preserve that kind of like local defect for future modification?
I think it depends